So that could be part of the improvement. In fact, we are slightly better. It sits about 54, 55. So if you keep yourselves to 54, 55, and with the weather improving, I'm sure that will happen anyway, then that might be okay for Mondays. I have posted the homework, but you can't access it because this is a university where if you don't know what you're doing, you can't get anywhere. So I can't figure out yet how to open it up for you guys to access it, but I will do that by the end of the day. But it's there, I have double checked. And I will cover this, the homework briefly, the contents of the homework today. It is due next Monday at 5 p.m. Hard copy or electronic copy, it must be either emailed to me or you bring it to my office. No delays. Now, as I mentioned, throughout the course you will be needing some form of software that will do the classical laminated plate theory. And one that is readily available to anybody in our aerospace engineering building is called Colibri. If you get on any of the computers in that building and you access Colibri, then you can use it. In addition, which goes with the book, there is a app for those who have iPhones or iPads, and because it's complicated to switch back and forth, I will not do the demo, but anybody interested during the break, you can come and I'll show you, or you can see how the app works, which does pretty much the same things. And we're now continuing. Today we'll also do engineering by compromise and voting engineering. You'll see if we can design something by voting and democracy, whether democracy is a way of designing structures, which we'll do in a little bit. We were talking about, we finished the classical laminated plate theory in terms of being able to calculate for a given laminate the stiffnesses and I use the plural because we have the membrane in-plane stiffnesses and the bending out-of-plane stiffnesses and coupling. And then based on those and applied loads, you can calculate strains and curvatures. And then we talked a lot about, we talked about failure criteria, which is the next step. You use all these strains and stresses to try to predict failure, because ultimately you want to design these structures for lower weight or for a bunch of other attributes that we will be covering today briefly. And in general, today's lecture is finishing up on some things we started talking about in the design process, as they are more specific to composites, but they are general enough that would be good to have in mind. And some of these aspects you will see in the homeworks and the final projects as we go through the course. Then we'll talk a lot throughout the course, briefly starting today, the fact that a structure can fail in more than one failure modes. In the standard metal structures, you know, you can have buckling or yielding, and you don't know in advance which is going to happen first. So in composites, it gets much worse. There's many more, and you can anticipate that by thinking of about the fact that you have fibers and matrix, and either of them can fail, or the interface between them can fail, and then in sequence can trigger different types of failure modes. And that, as a result, would make it more complicated, more challenging, and more interesting. And let me say up front that it becomes crucial to know the failure mode for which you are analyzing. If you don't know it, then you might miss it. This finite element code or whatever you are using is tailored to the construction that you made up, and it may not be able to tell you it's going to fail at this specific failure mode, and it might miss it. I'll show you examples throughout the course. Then we'll do the full-blown 17 equations in 17 unknowns for anisotropic elasticity, and we'll try to even start solving those for some relatively simple cases where we can solve them in closed form. So, having said all this as a background, we were saying that minimum weight is a big deal, but as a weight goes, you cannot simply minimize the weight if you pay no attention to the cost. And you've seen all kinds of comparisons between how much money one is willing to pay for every kilogram of weight saved, whether it's a space structure, which is much higher than an automobile, which is much lower. In fact, the numbers, just for now that I'm thinking about it, if you're doing your regular family car, then it's less than 2 euros per kilogram of weight saved that the manufacturer is willing to pay, because that translates to certain fuel savings and so on. If you're doing a higher performance car, but not Formula One yet, so it would be between the electrical cars and higher performance top of the line, then it's less than 6 euros per kilogram. Formula One approaches 20 to 50. Okay, so this is regular. This is higher performance. This is Formula One. Well, actually, depending on whether you are from Southern Europe, where money is no object, then it's more like 150 euros per kilogram. Now, if you have a regular civilian transport airplane, it's anywhere between 350 to 2,000 euros per kilogram, and the big difference here is based mostly on the anticipation of what the fuel prices will be in future years. That is, an airline today, or a manufacturer of an airplane today, has a certain impression of what the life cycle costs will be for that aircraft. And those are extremely strongly dependent on the fuel prices. And so there are today's fuel prices and what we think they will be in the future. And depending on where we think they'll go, then you can get numbers that can be in a quite wide range. And then, of course, space, the final frontier. Okay, so this one is civil transport. Then I can give you military. Starts at 1,000 and goes to, I've lived through a program which it was 15,000. This actually is an interesting story related to this. And then space is from 10,000 to 50,000 maybe, depending on, again, the specific application. Now, this is what usually happens is you have a program, you go through it, the design program, you start building, or you finalize the design and you realize most of the time that you're overweight. For 10,000 regions, the loads go up, the mission changes, your optimistic original estimates were wrong, and so on. So then the customer will penalize you, especially if it's military. Every kilogram you're overweight, the original weight, whether it's gross weight or weight empty. Then you have these huge efforts throughout the company designing, throughout the factory, to come up with lower weights. So, and they give incentives to the engineers, and they say for every, basically we pay you the amount that the customer is willing to pay. So I was in a program which was at 15,000 euros per kilogram of weight saved. So some of the stress engineers had been smart enough to have a little bit of a safety, extra safety factors in their designs, a slightly higher thickness, because the loads go up, because of whatever, anticipating and not wanting to have to the last minute to go and change everything. So it wasn't highly optimized, but it was optimized. So when they said, I'm giving you 15,000 euros per kilogram, these guys, showed up, and they were saving kilograms left and right, and they were making lots of money, because this was real money paid to their pockets. So on the one hand, if you are inefficient in your design, then people will tell you, you are not good enough, we don't want these kind of people because we're trying to save weight. On the other, if you are smartly inefficient in your design, you can make a lot of money. So cost is a big deal, therefore, and it can range, again, as I was saying last time, from the recurring, which is every time you make it, how much it costs you, labor hours, wear and tear of equipment. Non-recurring, which is the equipment, tooling, molds, and so on. Assembly cost, it's a very big deal, about 30% in a composite structure, about 30 to 45% of the recurring cost is assembly. So if you can minimize assembly, and by assembly we mean putting parts together, and that means minimizing the number of rivets, minimizing the number of parts or maximizing their size, so co-curing a lot of parts, that can really make a big difference. Low maintenance, the airlines are extremely interested in that, especially if you have composite airplanes where you have to retrain all your personnel to know how to do repairs, how to do inspection, and how to evaluate what they are doing. They have been working with metals for decades, and now it's composites. Replaceability across assemblies, I mentioned it last time, to be able to take apart from one aircraft and put it on another aircraft of the exact same model. It's not as easy as it sounds if it's not designed correctly. Natural frequency placement, zero coefficient of thermal expansion, and so on. Okay, that's what you try to do, and if you do everything, then it's great. If you do even one of them, it's still, in some cases and in some programs, extremely significant, especially the first two, the weight and the cost. So the structures consist of standard parts, and what I want to talk more about is going through some parts and talking about individual failure modes. If I have a standard skin, monolithic, which means that it's mostly a skin and it may have stringers or not, might be stiffened or not, then there's always the material strength as a possibility. Basically, you exceed the strength of the material, whatever that constituent it is that might fail, fiber or failure. But that is usually not even of interest, because you have to design the so-called damage-tolerant design. You have to design with typical damage present, because it's unavoidable that this will happen. So they have what we call the open hole tension, open hole compression, and then compression after impact, shear after impact, or even, in some cases, even though it's not that much of a driver, tension after impact. So once you put this kind of damage, you get a significant drop in strength. We'll see typical numbers and results later on today. And those become now a driver. But as if this were not enough, then you have all the stability related or buckling problems, and you can have the skin buckling as a whole, or the skin between stiffeners buckling, or the stiffeners buckling, and so on. Skin stringer separation, a fairly famous problem since the 787 issues that had stiffeners separating from the skin near terminating stiffeners. The huge mismatch of stiffness between a stiffener and the skin causes all kinds of problems. We'll cover that in a separate lecture further on down the line. Delamination, which is a fairly classical failure mode. Out of plane stresses develop even if you only have in-plane loads in some composite laminates. And then associated with rivets and fasteners, you have bearing failure, bearing bypass failures, inter-rivet buckling, and so on. Now, this is just a short list of what happens on a monolithic skin. Now, on the other side, if it were a sandwich, so this is the sandwich with a core in the middle, you still have the material strength, but now the face sheet or the core can fail, or the adhesive connecting them, so you have separate types of material strength failures. You still have the same notch strength concerns and buckling, and then all of a sudden you have specific failure modes to sandwich, and this is just an exercise in the English vocabulary at this point: wrinkling, crimping, intracellular buckling, delamination. This one, all these we'll see towards the end of the course when we cover sandwich separately. Failure modes on the one hand, on the other now you have to manufacture, and you have to come up with the best approach for the low cost, but at the same time to minimize your probability of failing in any given failure mode. For example, how do you attach a stringer to a skin? You can co-cure them, which means you are relying on the resin between the skin and the stringer to take the loads, the out-of-plane loads, and this may or may not be the best design. You can bolt them, and this is actually the strongest, but not necessarily the lightest. And because, as I was saying earlier, of the assembly issues, the assembly cost being related to how many fasteners or bolts you have to put through the structure, that could be driving your cost up. And then secondarily bonded, which means, okay, I'm not trusting my resin. It's not as strong as a regular adhesive, so I'm going to put some adhesive in between the stringer and the skin. The frames attaching to skins and stringers, the same kind of story. Then cutouts, if you have a window cutout or any form of a cutout, as you manufacture, you have to decide, do I want to make it without the cutout and then cut the cutout where I want it, or do I want to mold the cutout in, which means the mold itself will have special provisions such that I only place material around the location where the cutout will be. You can do either, and both of them have advantages and disadvantages. And every time you have a cutout, if it's a structure like a fuselage, or even not as much a wing, but the fuselage definitely, like the window cutouts and of course the door cutouts, you need to reinforce. And designing the reinforcement itself becomes an interesting problem, and the reinforcement itself will have a bunch of requirements related to manufacturing, and we will talk about designing reinforcements at the end of this lecture, if all goes well. Okay, stringers, stiffeners, or panel breakers, anything that's longitudinal, carries load along its main axis, and there's a bunch of different shapes that we are more or less all familiar with. I'm not going to go through them in detail. You'll see them later on throughout the course, some of them anyway. One aspect that I want to talk about now, and we will cover it in detail later, but I want it to appear as something you have at least seen once when we get to it in a few lectures, is that if I have a skin without any stiffeners, or if the stiffeners are extremely small so they don't add much stiffness, then under, let's say, compression, if I look at a section cut here, I will get the skin to buckle in a large, typically single half wave along the length and along the width. If I add stiffeners, and those stiffeners, which are meant to be those vertical lines shown here, and those stiffeners are stiff enough, they actually will stay straight when the skin buckles, and the skin will only buckle in between the stiffeners, and those little circles, gray and white circles, are meant to be positive and negative half waves coming towards us or going away from us. And in this case, the buckling load increases tremendously, so you can improve the performance by simply using the stiffeners as what's called panel breakers. They break the panel. They do carry some load. You don't need to make them stiff enough to carry a lot of load, but you can make them barely stiff enough to keep the skin from buckling in between the stiffeners. So that's just what it might look like in reality. You've seen those at the hangar anyway, I'm pretty sure. In more detail, for one-dimensional structure used in aerospace, you have the material failure, which breaks the structure. You have the column buckling, where you have basically the entire stiffener buckles in as a column shown here. You have a very localized local buckling, which is called crippling. We'll cover that in special lectures because it's a bit of a nightmare and extremely important. It occurs quite often. But then you can have an intermediate half wavelength buckling. So this is very short wavelength. And then if your fasteners are separated far enough and your flange is not stiff enough, then it will buckle just between them. And that's inter-rivet buckling. And I wonder why we can't get the rest of this. But okay. And then skin stiffener separation. Imagine the skin here between these two stiffeners. When it buckles, this part is meant to come towards us. And this portion is meant to indicate that it's going away. It's the half wave moving away. That means the skin itself tends to pull itself away from the stiffener, so you develop out-of-plane loads. We'll see those later on in the course. The frames are very similar in that as long as you isolate the longitudinal one-dimensional members, which are called caps, basically you have the outer flange, if you will, which is also called the outer cap, and the inner one, which are essentially these one-dimensional stringers or beams, whatever you want to call them, and they fall under what we just discussed in the previous slide in terms of types of failure modes. And you then recognize the webs constitute simple plates, and those can buckle or can fail in strength and so on. And of course, if you then have cutouts, you have to decide how you design the structure around the cutout. This is meant to be some kind of reinforcement here to give you both the buckling resistance that you might need and the strength, especially when it comes to local failure around the hole because of the stress concentration effect of the hole. Decks and floors are just glorified skins which can have different designs. Remember the stiffened design, the sandwich design, the grid stiffened design, and you can have both in-plane loads and out-of-plane loads, walking loads being one of the significant ones, and seat loads being another ones in the floor. And of course, impact loads, drop tools during maintenance, and so on. We'll cover impact on the second part of the course in a very, very much detail. Fittings. Fittings are these small gizmos that connect different parts. Therefore, almost by definition or as a rule, in many cases, they will carry load in three directions. As soon as you have load in a structure that's in more than two directions, that means there will be some part of the structure that sees out-of-plane loads. For a composite structure, that's a very important challenge, if not a problem, because the out-of-plane strength of the matrix used is so small that it makes it very difficult to design the structure without making it very heavy. Or if you decide, for example, to use fasteners or stitching to hold everything together, you make it very expensive. And usually there are these lugs. Basically, the fitting is meant to be this metal structure you can see here, and somehow, because of the requirement to connect, one of the best ways and most common ways is using lugs. A lug is basically this type of two-dimensional structure. Even a simple lug, and I think we'll see it later on, and I will pass one around, will have more than one failure modes. Even if you're loading only in one direction, longitudinal in this case, you can fail on either side of the load next to the hole, which is the net tension failure, or you can fail by shearing or shear strength being exceeded along these two lines. That's a shear out. Or you can fail by elongating the hole and failing ahead of the hole in bearing. And these failure modes compete with each other. In fact, one can lead to the other. Doors and covers, not much other than basically what I wanted to mention here more than anything else is the minimum gauge. As your structure, if your structure is very lightly loaded, then you can get away with such low thickness that you run into other problems. In composites in particular, because of the moisture absorption concerns, if you make your structure very thin, on the order of 2 to 3 plies, each ply being on the order of 0.15 millimeters, then over time, especially in a humid environment like the island of Guam, you will actually absorb a lot of moisture. This moisture goes through much more easily and can cause all kinds of problems, not only by reducing the local stiffness because the structure swells, but also because if you then freeze that water, that moisture, it expands and it can cause all kinds of additional problems. Well-known stories on the 737 horizontal stabilizers, which had been flying for decades. At some point, they took some of them off the aircraft and they sectioned them, and they found kilograms worth of water that had accumulated over the years, which had completely destroyed the core because that was a sandwich structure. But because it was a very conservative design, designed back in the late 70s, early 80s, I guess, it was still flying and performing quite well with minor aeroelasticity concerns because of the mass having changed, but it wasn't nothing that the pilots couldn't deal with. So the course is about taking the loads from somewhere, and for homework I will be giving you the loads most of the time, and the material properties, and then coming up with a structural configuration, which at the beginning can be anything based on previous experience, luck, your own intuition, or some intelligent way that you may have to come up with an initial configuration, such as the stacking sequence of a laminate, for example. Then you analyze this, and you need to make sure that it meets loads without failure, static and fatigue, and we won't be talking about fatigue, which is another very complex, interesting, and challenging problem in composites. And you try to minimize weight. Hopefully, you are also cost conscientious, if not explicitly trying to minimize cost also. And depending on the application, you may want to have additional attributes such as frequency placement, especially for helicopters, radar signature if it's on the military side. But very rarely your first configuration is your final one, and you need to iterate as you go through the analysis and finding either the structure is failing or it's not performing as you have wanted, and so on. And it's these iterations and automating or speeding up these iterations that's the biggest, most interesting aspect in all this. This one is just the same thing in block diagram form, so I'm not going to talk too much about it. There's a preliminary design, which can be a guess or a previous experience. Then you come up with a configuration, and around this configuration, doing some analysis, you will actually be iterating until you meet the loads and whatever other design requirements. And if you don't meet the desirable attributes, you have to iterate or you run out of time. So what does this mean, especially on the structure structural material and loads side. The applied loads that we take for granted, aerodynamic loads or whatever else, are never known extremely accurately, irrespective of how advanced your fluid dynamics, aerodynamics codes might be. You only can calculate those to within a certain approximation. And even if you have those reasonably accurately, whatever that might mean, translating those now to internal loads in your structure through, for example, some kind of a finite element model, again involves certain assumptions and certain approximations. As if this were not enough, a specific maneuver, which basically has an entry point and an exit point. You go into a turn, and then you come out of the turn back to level flight, let's say, will be flown by different pilots, or even if the weather conditions are slightly different, such that you will end up with different loads exerted on the structure. So if you are doing design, you have to account for this, and typically what you do is you simulate the structure, or you have some pilots fly it enough times with similar aircraft or know from previous experience to determine enough information to find the highest load or loads, depending on the types of loads, during that maneuver. And those highest loads, let's say the 95th percentile, you can then use to create the distribution shown here as a normal distribution. It doesn't have to be a normal distribution. But you take this distribution of the, I'm sorry, these are the highest loads. You take this distribution of the highest loads and the 95th percentile, or something along those lines, could be 90th, could be 99th, depending on the application, becomes your applied load, accounting for variability in how that maneuver, a 3G turn, might be flown, for example. Your material, even if it's supposed to be exactly the same day to day, coming from the vendor, will never be exactly the same. In fact, you buy it with a specific range in terms of properties, and the vendor guarantees that it stays within these properties, and if it doesn't, you reject it and you get new material and so on. So the raw material in and of itself has some variability because the microstructure is not consistent enough to give you the exact same stiffness, let's say, and the exact same strength. Manufacturing, especially if it's based on humans manufacturing, it involves all kinds of human error in terms of the sizes of the parts and how they are located, the orientation of the fibers. So that introduces error, and there are all kinds of other factors. Even if you were doing it with robots, you still have some variability. So that means you have a scatter in your specific properties, which will include this raw material variability, but it's also sensitive to, there's also one over there if you want. It's also sensitive to environmental effects, especially composites are much more sensitive to higher or lower temperatures than room temperature and the amount of humidity it's been absorbed. And of course, what kills everything, or what makes composites not the winner in every case, is the effect of damage. Any kind of damage that in a metal at most would be a little dent with localized yielded structure in a composite could reduce the strength by as much as 50%. So if you take all these, if you take material scatter, alone first, then, for example, this is typical tension strength data, and this is the strength in megapascal shown on the x-axis. Then the distribution of the tension strength is here. And for the exact same material, the distribution of the compression strength is here. Typically, compression is slightly less or significantly less than the tension. Obviously, you cannot take the average value, because if you take the average value, then there's a whole bunch of material that would be coming in with strength lower than the average that you could be using, and you had assumed the average value, and obviously you're being unconservative. So there are two values that are statistically defined, the so-called B basis and A basis, and those are the values we use for design, and they are in fact dictated in the design process by both the certifying agencies but also the manufacturers of the design. The B basis is the 10th percentile. Basically 90% of the tests you would ever do on that material would be higher than that value. And the A basis is the 1 percentile, so 99% of the tests you would ever do would have higher strength. Typically, the A basis is used for single load path primary structure. So if it's a blade and you lose the blade, you lose the aircraft, then that's an A basis design. If it's a skin stiffened structure and it's just a local failure, you can definitely redistribute the load, so it's like a multiple load path or slightly redundant structure. In those cases, you would use the B basis. And you will be seeing those in your homework. Environment, temperature. Increasing the temperature reduces the properties. So this is the temperature here, this is the cold temperature region, and this is the elevated temperature region. And this typically is the range that you would have to use to design in any flying contraption inside the Earth's atmosphere. If it's in space, then obviously the negative side on temperature is reduced by a lot. I have the tension as a function of temperature, and it's the continuous line, which you will see that around room temperature, then it starts dropping again. And the dashed line with the same color is meant to be the fully saturated by moisture set of properties. So if you actually leave the structure long enough in a very moist environment, you will run into all kinds of trouble because you have an additional knockdown because of the presence of moisture. Similarly, the two sets of curves here are for the compression side. When I was working in a program designing a all-composite airplane, the Starship at the time, we actually had to, this was 1980 through 84 through 1990, and it wasn't readily available, like climatic data around the world, so we actually had to contact physically the Meteorological Survey of the United States to give us information for the entire world, and we found that the most humid day in, day out place in the world is the island of Guam, which is actually pretty nice because it's 85% relative humidity. The only problem is that it stays that 360 days a year, you know, unlike Florida, which can get to higher humidity, but there are some days that are drier. And then the hottest place on Earth without any humidity is what? Do you guys know? Actually, by name. Yes, very good. Death Valley, it's ridiculous. I mean, on a really bad day, it can get like 100 degrees Celsius even. So the good thing is that it's dry. So if you were designing an airplane that would only be flying in the Death Valley, you would be using the continuous lines, and you would not have to worry about the humidity reduction.
Some of the cure temperature, some of the matrices are about 80 degrees. In that case,
that would be a bad matrix to use then. If your cure, I mean, basically you want to find where your glass transition temperature is, subtract like 10 degrees or so, and make sure your material is going to operate in environments that are at least 10 degrees below that. Or if you want to live with that, but nobody does it to my knowledge, you have to use extra reduction factors for material operating too close to its glass transition temperature. And that's, for a long-term performance in terms of fatigue loading, it's a bad idea because you will really be degrading the structure itself. So, for example, room temperature cure materials, you have to be careful if you intend to use them in very hot environments. So the damage on the other side, anything that you can do to the composite structure will actually affect it. So you can have things like holes drilled on purpose, lightening holes or fastener holes, or by mistake because you dropped some screwdriver it went through, or some madam dignitary with very spiky spike heels walking through the structure and it's very thin skins. It's happened, and it happens, and you have to design for that. But besides that, you have porosity, basically tiny voids distributed through the structure. You have delaminations, which is bigger voids, that are separation between the layers. And, of course, impact. And shown here, the most critical one, this is first generation thermoset composite materials, where the reduction, as you can see, can be down to 60% or more. Newer materials are significantly above this curve, but as a rule, the impact damage tends to be one of the most critical types of damage. So I now have to design my structure, and I have to recognize that even if it's pristine and perfect the day I make it, assuming the people on the shop floor were careful enough, which is not necessarily always the truth, then I have to account for the fact that it will be damaged during service, and I don't want it to be withdrawn from service immediately every time there is damage. And I have two types of requirements. One is damage that I can detect and damage that I cannot detect. Because in composites, even damage that we cannot detect, irrespective of the method you use for detection, causes a significant reduction in strength and to some extent also in stiffness. So if I can detect, we define this parameter, threshold of detectability, and that means that whatever method you chose, it may be able to detect a certain type of damage of a certain size, and if it's smaller than that, it's not reliable enough to detect it. So if you are right at that threshold of detectability, you have to design your structure to take ultimate load, because you have to assume that your structure at some point during its life will actually have that damage in it. And because you cannot see it and repair it, you have to live with it, which means it becomes an ultimate load requirement. Typically, the inspection method or the detection method is based on visible inspection, which is another interesting story. How many people looking at the same thing will arrive at the same conclusion in terms of, oh yeah, I can see the damage there and it's about that size. But that's what we have to live with. So if you choose that the inspection method is visible, then it's barely visible impact damage. So ultimate load for that, and limit load if it's visible damage. So you have to account for both, because sometimes if you design for limit load with visible damage, the knockdown at the limit load is bigger than multiplying that by 1.5 and comparing to your ultimate load. In other times, if you design for ultimate load for barely visible impact damage, then if you reduce by 1.5, you actually are already below limit load, so that is the driver. So you cannot do one of the two and assume you cover the other. You typically have to check for both limit load and ultimate, threshold of detectability, and visible damage. So if I take everything together, I will completely destroy this wonderful material that has these excellent properties. Basically, my strength at room temperature ambient and damaged is somewhere out here. And that's the mean value. Now, I have to reduce this from here to here, 5 to 20%, to account for the worst environmental effects. 5 to 20 depends on the property, depends on the material, depends on the environment you are taking into account. So you're down here, and then you further reduce it to include the worst type of damage. Typically, it's impact damage. And that gives you the mean strength at accounting for environment and accounting for damage. And then around that, we have the distribution. We said the material scatter has a certain distribution, and we'll have to go down here to use either the B basis or the A basis design value. So from here to there, materials which compared to steel would be no contest, would be the best materials in the world, all of a sudden become comparable in some respects. And to translate this to numbers, a typical material has a mean undamaged failure strain in compression of 11,000 microstrain, or 0.011. So if I apply typical knockdowns, these are typical, so don't take them for granted, even though you will see that almost everybody uses these typical, at least for preliminary design. For accounting for environment, we have 80% is the multiplicative factor, or a 20% reduction. Accounting for damage, barely visible impact damage, we multiply by another 0.65, or a 35% reduction. This is for the newer materials, not the first generation thermosets I just showed you, which are not as good as this. And then the material scatter to give us the A or B basis. This assumes a coefficient of variation. This at the bottom left here is meant to say CV, coefficient of variation of 11%, which is a bit on the high side, but it's good to cover most cases. Gives you another multiplicative factor of 0.8, or a 20% reduction. So if you take all these three together and you multiply by this 0.011, you will find 4,576 microstrain. And if you go and look at ever since the 70s, the typical cutoff strain values being used in composites were 4,500 microstrain. So there is a reason which is very much strongly related to this. So how does this therefore compare with standard materials? Aluminum, quasi-isotropic graphite epoxy, and then a graphite epoxy that would be more efficient than quasi-isotropic in compression. In fact, this is the stacking sequence given here. 45, minus 45, 0 to 90 with an overbar symmetric. 90 with an overbar means, for this course, that there's one ply in the middle and that's it. So the mid-plane is at the midpoint of that ply. If I were to write it, this is the full stacking sequence. So the mid-plane is here, and that's what the overbar means. The overbar means I only have 190, because if I didn't have the overbar, it would mean that I have two 90s next to each other and the mid-plane is in between the two of them. That's just for reference as far as this course is concerned. So stiffness, yield, compression, strain, and compression failure stress, and the corresponding values for the quasi-isotropic and for the graphite epoxy. And obviously, for the graphite epoxy, improved stacking sequence shown here at the bottom. Obviously, composites on a complete comparison in terms of actual absolute values are not as good. The saving grace is that they have significantly lower density. So if we do an example, and suppose I have some kind of a planar application, the weight, or the mass, I guess, I usually call it weight, officially it's the mass, is density times the thickness times the area, the planar area of that structure. So if I have failure, I know that the failure stress will equal my applied load divided by the cross-sectional area, width times thickness. So I can solve for this thickness, which is my applied force divided by the width times the failure strength. Now if I take this and I substitute in my weight expression to replace the thickness, I get an expression for the weight which involves the density and the quantity force divided by width divided by the failure strength. And if I'm to compare graphite or carbon epoxy materials to aluminum, then the ratio of the weights would cancel out the applied force, which we assume to be the same, and would cancel out the width because we're having the same planar area, and we'll end up with a ratio of density to failure strength. And if we use a quasi-isotropic material, then you will find that it's actually slightly heavier, 3% heavier than aluminum, and this is the typical black aluminum. Black aluminum design uses quasi-isotropic, which means the stiffness is the same in all directions, and it's not very efficient. If you use the more efficient design we just defined, then you are down to about 30% savings. So all of a sudden, the need to come up with the correct stacking sequence that will really take advantage of the composite capabilities becomes very important, because if you don't do it right, you will end up with either the same weight or, God forbid, even higher weight. Let's get together in 15 minutes, and again, if anybody wants to see the app, they can come in here. Iterations, let's see, where's my, let me jump to this one. It's the same thing with more words. Even if I could determine stresses and strains accurately, that's not even half the battle. I need to have a way to combine those in a failure criterion or something that tells me whether the structure fails and in what way it fails. And as I've already been mentioning, strength is only one of the many possibilities. In fact, some form of stability, local buckling or global buckling, will be most of the time the critical one. So you need to design, therefore, knowing what your specific failure modes are going to be. And that sounds as a self-fulfilling prophecy. If I know what I'm designing to, then it's easy to do it well. But if you don't know what you're designing to, then it's easy to fail. So that's why we test a lot and we analyze less. There's, in the last 10, 15 years, a much bigger effort to come up with improved analytical methods that are accurate enough to allow us to simulate tests, and there is some progress in that. But as I mentioned, there is the global buckling versus local buckling, both of which somehow have to be accounted for by your analysis. Then there's buckling of bays in between the stringers, or buckling of the entire plate, or buckling in between the grids in an isogrid. And then you have out-of-plane stresses that even if you have an in-plane loading situation, in many cases you develop out-of-plane stresses. We'll talk about those a lot later on in the course. And there, your finite element cannot really help you unless you have a fine enough mesh. But to know where to put a fine enough mesh means that you know in advance that the potential of a failure due to interlaminar stresses between the plies, that is in the out-of-plane direction, is high enough so that it justifies putting in a higher density. So, and that's just the beginning, and then if you think, okay, how do I model fasteners? Because if you don't model fasteners accurately, then you cannot predict bearing. How do you model accurately boundary conditions? What's the difference between simply supported and clamped conditions? We'll do some of that later on in the course. So here I have, again, a small case of a simple lug, which is loaded. In this case, it's loaded in tension. And I mentioned the failure modes earlier, so I repeat them now. You can fail by breaking on either side of the hole, and that's the net section failure. It's a tension failure. You can fail by bearing, which means that this hole in the center will elongate, and eventually, you see how much it has elongated here, and eventually you will fail now in tension in that case. Or you have a combined net tension and shear out. You can see the failure here, where the shear stresses locally are too high and exceed the shear strength. And as if all this again were not enough, and it's hard to see here, there's a big delamination, and you will see a similar case on the part that I'm going to pass around. This one was not loaded in the longitudinal direction, it was loaded in the transverse direction. But if you look at it closely, you'll see most of the failure modes. You will see that the hole has elongated in one of the two directions, which means there's a bearing failure in that direction. You'll see that the material has moved out of the way, you have local compression failure. And you will see, if you look at it on the edge, basically a huge delamination where the layers have separated. And by the time it goes all the way around, we will have a vote on what is the load to failure this. And the units we will use will be fully grown female elephants. The reason we're using this and not cars is because previous years I was using cars, so some people are catching up with the correct answer. So now, as this goes around and you see the failure, try to think how many elephants, female, because they are significantly lighter than male, it would take. So we are trying to define the parameters of the problem correctly. Sandwich, I mentioned it briefly. Here it is again. Here is a failed sandwich structure in compression. So these are the loading tabs going into the test machine, and you will see that it actually buckled. And buckling means there's a tension side and a compression side, and the point A here is the highest compression, which means you can fail the constituents such as the face sheet or the core or the adhesive in compression. At point B, you have the maximum shear, so you can fail the adhesive in shear or the core in shear. You don't often fail the face sheet in shear, but you could. And then, of course, the overall, what is wrong with this? The overall buckling, you can see it has buckled. And then you can have failure modes such as the wrinkling, which is a very localized buckling failure mode, and intracellular buckling, which is even more localized because it happens within cells, individual cells. All right, so if that's my background, then I need some equations, and the equations are here. I have equilibrium equations, which are these three equations, not including the body forces. Or the same equilibrium equations can be written in terms of the forces Nx, Ny, and Nxy forces per unit width, and the bending moments, and the shear forces Qx and Qy. These are out-of-plane shear forces. So either this set or that, not both, not necessarily both. The stress-strain equations, which for a single ply would sort of look like this, and notice I'm including the out-of-plane. In this case, I'm not integrating through the thickness. Or if I do it now for a two-dimensional case with integrating these through the thickness, I will have my standard classical laminated plate theory ABD matrix relating strains to forces and curvatures to moments. And then the standard strain displacement equations, which are here, and the curvatures here, which combine together with a linear distribution through the thickness Z, or zeta being measured through from the center midplane of the laminate. And you have therefore 17 equations in 17 unknowns, the 3 displacements, the 6 forces and moments, and the 2 out-of-plane shear forces, and then the 6 3 strains and 3 curvatures. So the whole idea is to solve those, and if you eliminate as many of the unknowns as you can, you will arrive into the 3 governing equations of anisotropic elasticity in terms of displacements U, V, and W. And these are coupled because of the B matrix. You see that the B matrix here is always multiplied in this equation by W. So what would otherwise would have been an equation involving only U and V picks up W here. The same for the second equation, which would only involve U and V again, but because of the B matrix you have this. Finally, the third one, which would have been only a D matrix times W terms. Because of the B, again, it brings in the U and V's. So for one thing, if we're trying to make our life easier, we should use symmetric laminates because the B matrix is 0, and that would make this to have no U and V dependence, and these two to have no W dependence. But good luck solving them anyway. It is extremely difficult, obviously. And there's a variation of those equations if you include, basically, if you're trying to do a buckling analysis, you have to include some kind of first order effects. And briefly mentioned here is how you would do the force equilibrium in the Z direction. And the book has complete derivation, or in much more detail. Basically, if you look at this equation at the bottom here, I have the D matrix with the force derivatives of W, and those are the same. Whoops, wrong way. That is the same equation here. If my B matrix is 0, then I will only have the W dependence. But in a buckling kind of problem, I pick up terms which involve my NX, NY, and NXY with derivatives of W, plus my usual out-of-plane loading. PZ is the load per unit area, and then Px and Py loads again per unit area in the X and Y direction. The actual details or first steps for determining that equation are shown here briefly. The book has much more detail on that. The point is that equation, we'll see it over and over again. So just remember D matrix times force derivatives of W for now, and we'll see it later on. Let's try to solve now these equations for some cases, not necessarily very simple, but of some interest to real structures. So the problem we're going to solve is this one, where I have a plate and I have a point load on one end and a distributed load on the other. And this is not just an academic exercise. It is very much related to the so-called problem of a stiffener termination. If I have a stiffened panel here, and those stiffeners, for whichever reason, they terminate, but the panel, the skin panel, let's say, continues on. They would terminate if there's not enough room. They would terminate if there's some other structure that has to go through there or be located there. As soon as they terminate, that means that locally now, if I isolate the portion of the skin with a stiffener at this end here, I would have this point load, or nearly point load, or concentrated load from that stiffener applied. Now I'm showing it as tension. It can be tension or compression. And at the other end, far enough from this termination, I would have the load fully distributed and transferred into the panel and being a uniform load. Now there's one slight thing here that I am omitting for now. Because the stiffener actually is loaded, let's say, along its neutral axis, then it's not simply an in-plane load here at the skin, but there's also a bending moment because of the load being eccentric. We are neglecting that, and we've done the solution. A master student has done that, so it's not that it cannot be done, but it takes a lot of algebra. Why are we doing this now? Is we're saying, okay, if I know that I'm going to have stiffeners terminating, most likely right where the stiffener terminates, which is at this location here, the skin, if I designed it just to take the load in the distributed form, would definitely not be strong enough. So I would need to reinforce the skin, and we select obviously to reinforce the skin locally, because making the skin, the whole skin, twice or three times as thick while it would work, it adds weight. So the challenge becomes to determine over which region from the load introduction here, the concentrated load, over which region measured by a length L and width W, will the stresses coming from this concentrated load be much higher than the far field stresses, and therefore would define the region that we would need to reinforce. So this is actually now becoming useful, because after all, ultimately we're interested in a design that would work, and one of the questions we would have to ask ourselves is, okay, how big of a doubler, how big of a reinforcement do I need in terms of a length and width? In order to do that, we need to determine the stresses for this problem, and we make some assumptions. It's a homogeneous orthotropic plate. The layup is symmetric, so the B matrix is 0. That the layup is balanced, so the A16 and A26 terms are also 0. That's just for algebraic purposes to make it slightly easier. And we are assuming there's no twisting, bending, coupling. We mentioned last time, I believe, that if you have anti-symmetric layups or layups using only 0s and 90s, or I'm telling you now, layups using only fabric material, plain with fabric preferably, then the D16 and D26 terms are 0. And we assume that the plate is sufficiently long and wide so the solution is not affected by the boundary proximity. Basically, as a first cut, we will assume this is long in this direction, so there's enough room for the stresses from the high value here to eventually go to their constant far field value, and the plate is wide enough so that whatever stress increase we have in this region will not reach the boundaries, because that would make the problem slightly more complex. These assumptions reminded me one thing I wanted to say. I keep mentioning quasi-isotropic, and just for purposes of definition, it's also in the text in the book. One way to create quasi-isotropic laminates, or the best way to create quasi-isotropic laminate, is to make sure that you have exactly the same number of fibers in every direction. But instead of having an infinite number of fibers distributed every degree, you can do it every certain intervals of degrees. So the quick way to do this is you take 180 and divide by n divided by 2. So that if you have n layers, you divide it by 2, you get 4. No, you don't get 4. I haven't told you what n is. The example in my mind is 8, but don't worry about it. If you have n layers, divide by 2, and then you divide that into 180. That tells you that you need fibers every so many degrees. So if the example says n equals 8, 8 divided by 2 is 4, 180 divided by 4 is 45. So you need to start from 45, then the next one would be 0, the next one is minus 45, and the next one is 90. Basically, those are the only angles that appear in multiples of 45 that will satisfy this. So a symmetric laminate that uses these in any combination or any order would be quasi-isotropic. So 45 minus 45, 0, 90, symmetric, is quasi-isotropic, but so is any permutation of these angles, 45, 0, minus 45, 90, and so on. If instead of n being 8, I had n equals 6, 6 divided by 2 is 3, 180 divided by 3 is 60. So any combination of 60 minus 60, 0 in a symmetric laminate configuration would give me a quasi-isotropic laminate. And you can change n to anything you want. It's just that after a while you will be getting fractional angles and so on. And if you're trying to think where I got this, 2 times 180 is 360. So I'm taking the full circle of going around, and I'm making sure that I divide it in equal intervals, and I have fibers in those equal intervals, which is the same. That's why where this comes from. So that was just a parenthesis, because I keep mentioning quasi-isotropic, and I meant to say that's one way of creating quasi-isotropic laminates. Stress-strain equations. This is the forces, and this is the A matrix with A16 and A26 equals 0. So we get this set of equations. And if I divide by the plate thickness capital H, then nx divided by h, as we said last time, is sigma x, and this becomes sigma y, tau xy. And then all these just get divided by h. We assume that there's no dependence on the z-coordinate out of plane. Basically, it's a plane stress kind of problem, so all the derivatives with respect to z are 0. So my equilibrium equations, which had, the first one had d tau xz dz here, is not there. D tau yz dz here is not there. And the full third equation, as shown back here, where are my equilibrium equations? Here. So in these equilibrium equations, the last terms of the first two equations and the entire third one, which involves the out-of-plane stresses, disappeared. So that's what simplified things over there. So if I solve for the strains from my stress-strain equations, I get these expressions for the three strains. Now, my strain displacement equations, this moves up, yes. Remember, epsilon x is du dx, epsilon y is dv dy, and gamma xy is du dy plus dv dx. Now, these are three equations in the two unknowns, if you want to call them, u and v. So I can actually eliminate u and v and arrive to a single equation that will only involve epsilon x, epsilon y, and gamma xy by taking appropriate derivatives here. And you can show that, or you can find it in the book, or you can take my word for it. This is the answer. When I eliminate from these three equations u and v, I arrive at the classical compatibility equation that only involves the strains. But I know the strains calculated here, so I can substitute into this equation for those strains to get this, which now involves the stresses. And now I have the equilibrium equations that I just showed you at the bottom here, two equations. So I can eliminate two of the stresses in this last equation here to arrive to a single equation that will involve only one stress. In this case, it's the sigma x stress. X, notice this is my xy coordinate system, so x is pointing down in the plate that we have there. Fourth order partial differential equation with beta and gamma as defined here. And this is one of the cases where you can solve it exactly using infinite series. The boundary conditions for the problem tell us that at this top surface here, x equals 0, my sigma x stress is 0 everywhere except for the middle point location, where it will actually equal my applied force divided by the local cross-sectional area, h the thickness of the plate, and little h the width of the region, let's say of the flange of the stiffener, or the width over which this load is applied. Then at the other end, I have sigma x at x equals a, which is a constant value. And then sigma y at the two vertical edges is 0, and tau xy everywhere on all the edges is 0. So I have to solve for this, and I think, yeah, let's do some of the solution, but we will stop and then we'll do the homework. Where's the little gizmo, the lug? But it took 15 minutes to do like 30. Okay, you guys had better have good answer though, because it took so much time. All right, yeah, we still have time, but keep on moving it. I assume that the solution will be some function of x times cosine n pi y over b, for reasons that will become obvious in just a little bit. If I use this and I substitute in my governing equation shown here at the bottom, then the y dependence disappears because I have even derivatives of y, so the cosines reappear, and I'm left with a single equation on x, an ordinary differential equation, fourth order on x, which from standard differential equation theory, it's in terms of exponentials with the exponents. 4 exponents, plus or minus here and plus or minus there, means that I have 4 different exponents. Now, in general, there's nothing that keeps the beta squared from being smaller than 4 gamma. So this quantity under the square root, or this quantity under the square root, could be negative. So the solution could be complex. There's nothing that keeps complex conjugates from appearing, and that means you get decaying exponentials and increasing exponentials as part of the solution. If I just take this now blindly and I combine with my expression here and recognize that this n, which appears there, it can be anything, any integer, then it becomes an infinite series. So I will have this form to represent this, plus a constant, because this constant k0 also satisfies my equation if the stress was k0, and because these are all derivatives, obviously the constant will disappear. Why do I add the constant? Because what I'm using here is what's called a Fourier cosine series, and I know from the theory of the Fourier cosine series that I need a constant to recover the average value of the stress I'm trying to approximate. anybody that's still with me may have noticed that I said there are 4 phi values here, and I've only used 2 of them. That's because I'm making an assumption, hopefully it's on the next page. Yeah, I'm making an assumption that the plate is long enough, and therefore, if it's too long, these positive values of phi with positive real parts would actually explode, and therefore are not part of the solution. There are no infinite stresses. And I'm using only the ones, therefore, that have negative real parts, which would be 2 of them in general. If my plate is short, what do I mean by short? If the distance between this edge and that edge, or the length A, is very short, then those exponentials with the positive real parts don't have enough time to become infinite, and therefore I would need to include them. And in fact, you can play a game and keep changing the value of A and solving using all 4 exponentials, and all of a sudden you will find that after a while only 2 of them are what you need if it's A is too large, and you will need all 4 of them if A is too small. So for now, let's say it's long enough, and that means I will only use the 2 phi values, and I'm adding the constant K0 again from the theory of the Fourier series, because I need it for reasons that will become obvious in a second. Having determined sigma x, I can then use my equilibrium equations to determine sigma y and tau xy, which this is just straight differentiations and integrations from this expression here. Notice that when I do that and I check for my boundary conditions, if y, let's look at sigma y here, if y equals 0, then I get 1 minus 1 is 0. Sigma y is 0 at y equals 0 on this edge, which it is. And if y equals b, then cosine 2n pi is again 1. 1 minus 1 is 0 again, so it's 0 at the other edge. This is the reason why these appear as even. N becomes 2n, so that both on this edge and on that edge I can satisfy the boundary conditions for sigma y. Similarly, if you take the tau xy expression and you check its values at the 4 edges, you will find that it's 0, so it satisfies the boundary conditions. And what I still haven't satisfied are the boundary conditions on sigma x. Basically, I haven't clearly imposed the condition that at this edge sigma x is 0 and all of a sudden jumps, and then it's 0 again. To do this, it's just a direct Fourier series determining the nth or the nth term of a Fourier series. Basically, K0 is by definition of Fourier series the average of the function sigma x at any x location. And that average is just the force divided by B times h, the thickness of the plate. So this, the total force divided by BH, is the average stress, and that's what this quantity, sigma x, should be at any x location. If I make a cut along x, I should still find the same value for the average, and you can check that by integrating. You'll find that the y dependence disappears and you are left with f over bh. Now, that gives me the average, but I still have to reproduce this type of shape for the stress at x equals 0. 0 for most of the edge, and then it jumps to the applied local load and then comes back down to 0. That means you take that function, you integrate it from here to there after you multiply by cosine 2q pi y over b. Do the same thing on our Fourier series, and when you do that, you could eventually determine that this will only work if an is given by this quantity. That's standard Fourier series. If anybody is having trouble, come to my office and we can show it in detail, but basically it uses the fact that cosine 2n pi y times cosine 2q pi y will integrate to 0 unless and only unless n and q are equal, from which you will pick up only one term from this series instead of the infinite series, the one when q and n are equal, and that will give you your an. So let me stop here for now. We'll see how good the solution is next time, but I need to talk about the homework. And where's the little thing going? Okay, we still have some time to go. Let me bring up the homework now. Homework 1. Guys at the back can see this, or should I make it larger? Okay, so, okay, I'll make it larger. It wasn't as enthusiastic of it's okay that you guys said so. So, we have a rectangular laminate, and this is the stacking sequence, 45 minus 45, 0 symmetric, which means 45 minus 45, 0, 0 minus, whoops, 45 and 45, and that's the entire laminate. So there's another 6 plies. So, and it's under pure torsion. So for those of you who thought that after the second year torsion and Prandtl stress functions you were done, I'm avenging myself on you here. And the twisting moment, mxy, or the torque T, is 44.48 Newton millimeters per millimeter. Remember, these mxy are, in classical laminar plate theory, are per unit width. So these are per width, per millimeter width. And why the value is obscure is if you actually translate this to English units, it will be a very nice round number, but still I'm using English units because of my background. So that's the applied load. We are told that the out-of-plane deflection W for this laminate is 0 at x equals y equals 0, and that the first derivatives, dw dx and dw dy, are also 0 at the same location, both at x equals y equals 0. This means this is my rectangular laminate, x going through the center, y perpendicular here, and I have my torsion load. W is measuring deflection out of plane. You are supposed to determine the actual shape of W, so you have to tell me exactly how this deforms and plot this W. Now, for the plot, you will assume, and only for the plot, I don't want the answer for W to include these dimensions. I want them in terms of A's and B's, and then only in the end you substitute. So the length is 10 centimeters along X, this dimension here, and the width is 5 centimeters. And if you cannot do a 3D plot, then that's okay, but I want then a plot of W as a function of Y at X equals -2, x equals 0, +2, and +4. So at different locations, you will plot exactly what the shape is as a function of y, so I can tell that you got the right shape. Having done all this, then you go to part B. Determine the value at which the laminate fails and the type of failure. So Colibri or whatever else you want to use, you apply this load, and you have to tell me what's the maximum value mxy. So it may not be 44.48. The 44.48 is just so that when you do the plot later on, we'll have some actual shapes to compare. But find at what value of mxy you get failure, which ply fails, and in what form. Is it a transverse tension, compression, shear, or if you use more advanced failure criteria that differentiate between fibers and matrix. If you can tell me that, that's not necessary, but I would definitely will want to hear from you. It's failing because in the direction perpendicular to the fibers, in compression, this ply has failed, or whatever it is. And at failure, you will tell me exactly where that is, not just the ply, but you will tell me whether it's the middle of the ply, the top of the ply, the bottom, where through the ply thickness it happens. I want the pinpoint accuracy on this one. And what is the maximum strain? Now there are 3 strains, epsilon x, epsilon y, gamma xy. I want you to just look at the 3 strains at that location and find the one that has the highest absolute value. So if epsilon x is 10,000 and epsilon y is 3,000 and gamma xy is 3,000, the answer is 10,000 for that part. Just tell me of those, which one is the largest. Why am I doing that? Because I think when you look at it, you will observe one of them is much larger than the others, and by forcing you to observe it, then maybe you will remember that in problems of this kind, typically one of the strains, the one that you are going to report to me, is much higher than the others. Give only the highest of the 3 strains. Okay. Any questions so far on this? I'll give you material properties. X is parallel to the fibers for the material we are talking about. Y perpendicular. This is Poisson's ratio, shear modulus, thickness of the ply, and then tension compression parallel to the fibers, tension compression perpendicular to the fibers, and shear. Now that's classical laminar plate theory, basically, and first ply failure, and a little bit of math to give me the shape of W. Now there's one more problem, where we say, okay, we actually tested this laminate now, but we did not test it at room temperature. We tested it at the elevated temperature wet conditions. And we found that it failed at half the load that you predicted in part 1, because part 1, for one thing, includes only room temperature values, doesn't account for the fact that it's conditioned with moisture, fully saturated with moisture. So if there were no damage in the specimen, but someone told us this is an A basis specimen, so it's at the low end of the material strength, 1 percentile of the population, then you are supposed to somehow tell me what is two things: the coefficient of variation. Coefficient of variation is standard deviation divided by the mean. And two, the B basis of the critical strength property, whatever is the failure mode that we said on the previous problem. If it's transverse tension, let's say I want you to calculate the coefficient of variation and the B basis for transverse tension at room temperature ambient. Now, any material we've shown in the course, and you will need some of it, is fair game, because there's moisture issues and you need to estimate or decide how much of a strength reduction moisture causes alone, let's say. So you can use any of the charts that have been in the course, not any charts from elsewhere. I'm sure you can find elsewhere other things, but I want you to stick to what we have presented in the course. This involves some knowledge of statistics, but you guys had better have taken statistics courses. So assume normal distributions, and then you should be able to relate anything and everything. You can basically, you will need to find percentiles, first percentile, 10th percentile, and so on, for a normal distribution of a known mean and standard deviation. Excel does it automatically, so you can do it whichever way you want. If you get in trouble, you can let me know. You know where to find me. Are there any questions? Going once? Yes? Yeah, either the book or the lecture, but those two only. And I will make sure, but by tonight, that the homework problem is actually accessible, because I have posted it, but I don't know how to open it up for access to you guys. Yes?
The drawing looks like the center of the coordinate system is in the center of the plate.
Yes.
Does that mean that there the displacement in the slope is 0?
Indeed. Well, think about it. If you had a piece that you were twisting, smack in the middle, if you're twisting, it would be 0. Of course, for our problem, it will be interesting. That's why I want you guys to plot it and see what you guys observe, but I'm not asking you what would you guys observe. We'll see if anybody observes anything, then I will give bonus points. Okay, any other questions related to the homework problem? It's due next Monday. Now, how many of you think that this would fail at one fully grown female elephant being hanging off this in this direction? Raise your, say again? African. Good point. African. African female elephant. Anybody thinks it's going to be less than or equal to 1? I'm not sure if that's good or bad. We'll see. Anybody thinks it's between 1 and 3? Okay, now I have to count, obviously. 1 and 3, 17. Between 3 and 5. Wow. No double votes, right? You voted before. No, you did. 30. Cool. 34. Anybody thinks it's more than 5? Brave guys. 6. Okay, the answer is here. So majority actually wins. I think designing structures by majority works. And that's a message to take home. Of course, if you want to see how to estimate or calculate this, there's a whole chapter in the book, chapter 9 or something, but that covers entirely lugs and failures in different directions and how you come up with stacking sequences and everything. But I'm encouraged. Not every year do the majority actually wins it, designs it correctly. So this is very good. In fact, the exact answer is a little less than 4 female, or so it would be 3 plus 1 on a diet would be the elephants. Okay, I will see you on Friday. So that could be part of the improvement. In fact, we are slightly better. It sits about 54, 55. So if you keep yourselves to 54, 55, and with the weather improving, I'm sure that will happen anyway, then that might be okay for Mondays. I have posted the homework, but you can't access it because this is a university where if you don't know what you're doing, you can't get anywhere. So I can't figure out yet how to open it up for you guys to access it, but I will do that by the end of the day. But it's there, I have double checked. And I will cover this, the homework briefly, the contents of the homework today. It is due next Monday at 5 p.m. Hard copy or electronic copy, it must be either emailed to me or you bring it to my office. No delays. Now, as I mentioned, throughout the course you will be needing some form of software that will do the classical laminated plate theory. And one that is readily available to anybody in our aerospace engineering building is called Colibri. If you get on any of the computers in that building and you access Colibri, then you can use it. In addition, which goes with the book, there is a app for those who have iPhones or iPads, and because it's complicated to switch back and forth, I will not do the demo, but anybody interested during the break, you can come and I'll show you, or you can see how the app works, which does pretty much the same things. And we're now continuing. Today we'll also do engineering by compromise and voting engineering. You'll see if we can design something by voting and democracy, whether democracy is a way of designing structures, which we'll do in a little bit. We were talking about, we finished the classical laminated plate theory in terms of being able to calculate for a given laminate the stiffnesses and I use the plural because we have the membrane in-plane stiffnesses and the bending out-of-plane stiffnesses and coupling. And then based on those and applied loads, you can calculate strains and curvatures. And then we talked a lot about, failure criteria, zero coefficient of thermal expansion, and so on. Okay, that's what you try to do, and if you do everything, then it's great. If you do even one of them, it's still, in some cases and in some programs, extremely significant, especially the first two, the weight and the cost. So the structures consist of standard parts, and what I want to talk more about is going through some parts and talking about individual failure modes. If I have a standard skin, monolithic, which means that it's mostly a skin and it may have stringers or not, might be stiffened or not, then there's always the material strength as a possibility. Basically, you exceed the strength of the material, whatever that constituent it is that might fail, fiber or failure. But that is usually not even of interest because you have to design the so-called damage-tolerant design. You have to design with typical damage present because it's unavoidable that this will happen. So they have what we call the open hole tension, open hole compression, and then compression after impact, shear after impact, or even, in some cases, even though it's not that much of a driver, tension after impact. So once you put this kind of damage, you get a significant drop in strength. We'll see typical numbers and results later on today. And those become now a driver. But as if this were not enough, then you have all the stability-related or buckling problems, and you can have the skin buckling as a whole, or the skin between stiffeners buckling, or the stiffeners buckling, and so on. Skin stringer separation, a fairly famous problem since the 787 issues that had stiffeners separating from the skin near terminating stiffeners. The huge mismatch of stiffness between a stiffener and the skin causes all kinds of problems. We'll cover that in a separate lecture further on down the line. Delamination, which is a fairly classical failure mode. Out of plane stresses develop even if you only have in-plane loads in some composite laminates. And then associated with rivets and fasteners, you have bearing failure, bearing bypass failures, inter-rivet buckling, and so on. Now, this is just a short list of what happens on a monolithic skin. Now, on the other side, if it were a sandwich, so this is the sandwich with a core in the middle, you still have the material strength, but now the face sheet or the core can fail, or the adhesive connecting them, so you have separate types of material strength failures. You still have the criteria, which is the next step. You use all these strains and stresses to try to predict failure, because ultimately you want to design these structures for lower weight or for a bunch of other attributes that we will be covering today briefly. And in general, today's lecture is finishing up on some things we started talking about in the design process, as they are more specific to composites, but they are general enough that would be good to have in mind. And some of these aspects you will see in the homeworks and the final projects as we go through the course. Then we'll talk a lot throughout the course, briefly starting today, the fact that a structure can fail in more than one failure modes. In the standard metal structures, you know, you can have buckling or yielding, and you don't know in advance which is going to happen first. So in composites, it gets much worse. There's many more, and you can anticipate that by thinking of about the fact that you have fibers and matrix, and either of them can fail, or the interface between them can fail, and then in sequence can trigger different types of failure modes, and that, as a result, would make it more complicated, more challenging, and more interesting. And let me say up front that it becomes crucial to know the failure mode for which you are analyzing. If you don't know it, then you might miss it. This finite element code or whatever you are using is tailored to the construction that you made up, and it may not be able to tell you it's going to fail at this specific failure mode, and it might miss it. I'll show you examples throughout the course. Then we'll do the full-blown 17 equations in 17 unknowns for anisotropic elasticity, and we'll try to even start solving those for some relatively simple cases where we can solve them in closed form. So, having said all this as a background, we were saying that minimum weight is a big deal, but as a weight goes, you cannot simply minimize the weight if you pay no attention to the cost. And you've seen all kinds of comparisons between how much money one is willing to pay for every kilogram of weight saved, whether it's a space structure, which is much higher than an automobile, which is much lower. In fact, the numbers, just for now that I'm thinking about it, if you're doing your regular family car, then it's less than 2 euros per kilogram of weight saved that the manufacturer is willing to pay, because that translates to certain fuel savings and so on. If you're doing a higher performance car, but not Formula One yet, so it would be between the electrical cars and higher performance top of the line, then it's less than 6 euros per kilogram. Formula One approaches 20 to 50. Okay, so this is regular. This is higher performance. This is Formula One. Well, actually, depending on whether you are from Southern Europe, where money is no object, then it's more like 150 euros per kilogram. Now, if you have a regular civilian transport airplane, it's anywhere between 350 to 2,000 euros per kilogram, and the big difference here is based mostly on the anticipation of what the fuel prices will be in future years. That is, an airline today, or a manufacturer of an airplane today, has a certain impression of what the life cycle costs will be for that aircraft. And those are extremely strongly dependent on the fuel prices. And so there are today's fuel prices and what we think they will be in the future. And depending on where we think they'll go, then you can get numbers that can be in a quite wide range. And then, of course, space, the final frontier. Okay, so this one is civil transport. And I can give you military. Starts at 1,000 and goes to, I've lived through a program which it was 15,000. This actually is an interesting story related to this. And then space is from 10,000 to 50,000 maybe, depending on, again, the specific application. Now, this is what usually happens is you have a program, you go through the design program, you start building, or you finalize the design and you realize most of the time that you're overweight for 10,000 reasons. The loads go up, the mission changes, your optimistic original estimates were wrong, and so on. So then the customer will penalize you, especially if it's military, every kilogram you're overweight the original weight, whether it's gross weight or weight empty. Then you have these huge efforts throughout the company designing, throughout the factory, to come up with lower weights. So, and they give incentives to the engineers, and they say for every, basically we pay you the amount that the customer is willing to pay. So I was in a program which was at 15,000 euros per kilogram of weight saved. So some of the stress engineers had been smart enough to have a little bit of a safety, extra safety factors in their designs, a slightly higher thickness, because the loads go up, because of whatever, anticipating and not wanting to have to the last minute to go and change everything. So it wasn't highly optimized, but it was optimized. So when they said, I'm giving you 15,000 euros per kilogram, these guys, showed up, and they were saving kilograms left and right, and they were making lots of money, because this was real money paid to their pockets. So on the one hand, if you are inefficient in your design, then people will tell you, you are not good enough, we don't want these kind of people because we're trying to save weight. On the other, if you are smartly inefficient in your design, you can make a lot of money. So cost is a big deal, therefore, and it can range, again, as I was saying last time, from the recurring, which is every time you make it, how much it costs you, labor hours, wear and tear of equipment. Non-recurring, which is the equipment, tooling, molds, and so on. Assembly cost, it's a very big deal, about 30% in a composite structure, about 30 to 45% of the recurring cost is assembly. So if you can minimize assembly, and by assembly we mean putting parts together, and that means minimizing the number of rivets, minimizing the number of parts, or maximizing their size, so co-curing a lot of parts, that can really make a big difference. Low maintenance, the airlines are extremely interested in that, especially if you have composite airplanes where you have to retrain all your personnel to know how to do repairs, how to do inspection, and how to evaluate what they are doing. They have been working with metals for decades, and now it's composites. Replaceability across assemblies, I mentioned it last time, to be able to take a part from one aircraft and put it on another aircraft of the exact same model. It's not as easy as it sounds if it's not designed correctly. Natural frequency placement.